Now we're going to launch a projectile at an angle from ground level, and it's going to return to ground level over here. I still have the velocity vectors turned on so we can see what's happening in the vertical and horizontal directions. I have my angle set at 65 degrees here and my initial speed at 15 meters per second. Got the speed turned down to slow, so let's watch what happens. I'm going to freeze this every now and again so you can see here now. This is the vertical component of the overall velocity. So this is the direction that the ball is traveling in. If we could extend this out here, I don't know if this will work, but there we go. So there's the overall velocity vector. I don't think I can show the two of them at the same time, but here is that velocity vector broken down into components. It has a horizontal component and a vertical component, and together they add up to give you this overall velocity. So here's how fast that ball is moving sideways, and here's how fast it's moving up and down at that moment in time. If we allow this to continue, you can see what happens. The horizontal component of the velocity has not changed. It stays exactly the same the whole time that it's in flight. If we get rid of air resistance, that's what happens. But obviously, as it's rising, the vertical component of the velocity is starting to decrease. Let's allow this to go all the way up to, there we go. So now it's at the top of its flight. The vertical component of the velocity has dropped to zero, but it's still moving sideways. So it does have a horizontal component that never goes away. And now it's going to start to fall, and you can see that the vertical component of the velocity starts to grow in the downward direction. Now the vertical component of the velocity is negative if we've chosen upwards as our positive direction. The acceleration would always be downwards, but the horizontal component of the velocity has not changed the whole time. And we go over here, and then by the time we hit the ground, there's our impact, and you can see that this is a symmetrical parabola, which means that the vertical component of the velocity, I don't know if this will work. Okay, I allowed it to hit the ground. That was probably not a good idea. But the velocity, the overall velocity at impact is the same as the overall velocity at launch, except that it is the direction has changed. The vertical component here is up. Here the vertical component is down, but they're exactly the same. And the horizontal component doesn't change throughout the flight. So just watch the two green arrows. The horizontal component never changes. The vertical component is in a continual state of flux. And there you go. Now, if you want to find out how long that ball is going to be in the air, you really have to completely ignore the horizontal component of the velocity. The only thing that matters is the vertical component. So if we multiply the 15 meters per second by the sine of 65, that's going to be our V1. So let's see here. Now I probably should have had that done beforehand. So 15 times the sine of 65 is 13.6. Now I can't get that exactly at 13.6, unfortunately. But so around 14. And if I do this again and put the angle here, this should be very similar. The up and down motion should be very similar to this parabolic arc. So let's have a look. It'll go up a little bit higher because that's a little bit higher than 14, but it's pretty close. If I had set this at 13.6 meters per second, it would have risen to the exact same height. It would have been in the air the exact same amount of time as this ball that was launched sideways. If you want to find out how far sideways it goes, all you need to do is find the horizontal component of the velocity, which in this case would be, it would have been 15 times the sine of 60, sorry, the cosine of 65. So sideways, it was going 15 cosine 65. It was going 6.3 meters per second times 2.77 seconds. And that will give you the range. The time in the air you can find using the vertical component of the velocity, and the horizontal range you can find by multiplying the time in the air by the horizontal component of the velocity.